Bismillahirrahmanirrahim. Welcome to the new session. Today our presentation is about the cantilever slab design. We will discuss briefly and in detail about the structure design of cantilever slab, its analysis, how to check its shear capacity and its deflection, and then the reinforcement placement, required reinforcement, steel requirement, the thickness requirements, and the material properties. So starting from a simple cantilever slab, this is a typical model. Suppose we have a slab of 10 feet span, cantilever span, okay, and we have imposed load on the slab, as well as on the edge we have a wall, and that wall applies a load, a point load on the slab as well. So we will calculate first of all these loads, then we will calculate the moments, and then flexure requirements, the steel, area of steel, then the spacing of the steel required for this slab, and then we will check its shear capacity and deflection. So suppose we this the span is 10 feet, as we discussed. You can make it more 12 or 15 as well, but suppose we are using this one as 10 feet span. The dead load, imposed load is 40 pounds per square feet. Then live load is 40 pounds per square feet. We can make it at 60 as well. Suppose the live load is 60 pounds per square feet. This is the span, and the material properties we are using is like FC prime. The concrete compressive strength is 2.5, or you can make it 4 even, don't worry. Like if suppose someone has some mixed ratio, according to the mixed ratio the strength is 4000 psi, so you can make it 4. Or usually in cantilever and in the long span structures we use this 4000 psi strength. So let's use here 4000 psi strength, 60 grade steel. Then these properties are automatically calculated. This modulus of elasticity is the calculated as per 57,000 into under root FC prime. So this is the value. Then gross moment of inertia. Minimum slab thickness required as per ACI is length of the cantilever span divided by 10. So according to the formula, minimum thickness required is 12 inches, 1 feet is required, and we provide the same 1 feet, 12 inches. Okay, clear cover automatically will be calculated, the thickness minus the clear cover minus the bar provided by 2. This is the clear cover, sorry, the clear, no, sorry, not the clear cover, this is the clear depth. This is the depth, effective depth, so this is 11 inches, sorry, this is inches. Okay, this is inch 4, and this is psi. Okay, these are the units. This is the inches. Okay, now self weight of the concrete is calculated like this: 150, this is 12 by 12 into 150, this is 150, 0.15. This is in kips. per cubic feet, pounds per cubic feet. This factor load is 1.2 into dead and plus 1.6 into live load. This is factor load, and this is the point load here. We discuss here that sometime wall is provided on the edge of cantilever portion, so we have to calculate this one as well. Okay, so this is the load superimpose, and this is the cantilever portion load. So the moments due to this load, this factor load are like UDL or uniformly distributed load will be calculated, and then the moment due to this edge wall point load will be calculated. Coming to the calculation, the analysis, the moment due to uniformly distributed load is 16.2 kip. Okay, and in inches this is 94.4 kip inch, and this is the point load. This is the moment due to the point load 105.6. Okay, the total load moment is 25, and this is 300. Coming to the calculation, starting we will calculate. This is very famous formula for the A. So I have put this formula here. Like every engineer should know about this, that A is equal to as F by 85% of FC prime B. This should be happens to all, like memorized by heart to each and every engineer, that A is Fy by 0.85 FC prime B, and this is the area of formula for area of steel. Moment, the factor moment divided by this pi Fy d minus Fy2. This formula. So this making the trial and error calculations. A is this, and A is area is this one. So finally we get 0.33 for the uniformly distributed load, and 0.018 for this point load moment. So adding both of these comes to be 0.51. So this is the total area required for the slab, inches per inches. This is in the area. Okay. Now come to the AS minimum. A minimum area should be calculated. This is very required, because suppose if the calculated area is less than the minimum, so we have to provide minimum. So this is 0.0018 into B into H, and this is compared. So if AS is less than AS minimum, then provide AS minimum. But here the case is not here like this, because the area is more than this one. Then coming to the steel calculation, for the bar calculation, suppose I have put 3 or 4 bar option. If someone is using number 3, so he has to provide 3 inches spacing. This which is not recommended and not allowed by the code as well. Then if number 4 bar is used, so provide 5-inch spacing. If number 5, 7-inch spacing, and if number 6 bar is used, so 10 inches spacing. Practically, I will recommend to use number 4 at the rate of 4 inches, or number 6 at the rate of 8 or 9 inches. Okay, this is practically. This is 8 inches and this is 4 inches. Practically, so if I want to like apply, because we have to be more safe. Reducing the area by the spacing, reducing is like going to more safer side. Okay, now maximum area we have to calculate as well. The maximum area required is 2.6. We cannot exceed this area. Okay, I have made it red like this is alarming, that do not exceed. Some engineers, like in the beams, put too much steel, in the slab put too much steel, so they exceed this limit. So the structure goes to the brittle failure. The steel has this beauty that if it should be fair, like yielding should be started before concrete, so that the structure can give you warning. There are some hair cracks or small cracks. It means that the structure is going to be failed, but he is giving to you a warning that please save me, save me, save me, because I am going to be failed. So this is the beauty of the steel, and this is the beauty of the RCC structure, that it doesn't go to the failure suddenly. It starts with hair cracks, then with propagating with a little bit more, then more than one, and finally the deflection and the cracks are appeared. So during this period, it's enough period for the engineers to restore, or like to make some good arrangement, to make the structure strengthened, to make the beams or the columns or the slab retrofitting. So retrofitting is also a good technique if there's some cracks. So this is another topic, but just to tell you that maximum area should not be like crossed. Some people give the depth of the beam is less, and they provide steel, more steel. So the concrete is less and the steel is more, so that the structure goes to the brittle failure. This is not recommended. Okay. This is the maximum, which is not recommended, not recommended, not recommended. Okay, all not recommended. One. So this is just for food for thought, that we should not exceed the is maximum. Maximum spacing allowed is 24 inches. We are not crossing this one. Okay, and the minimum spacing required is 3.6 inches. We are not using this one as well. So this is just for information. So this is the flexure design is done. Now you can provide the steel detailing. So the detailing is simple. Right, provide the main reinforcement at the rate of number 4 at the at 4 inch center, and the shrinkage reinforcement provide with the S minimum. Shrinkage reinforcement for like the main reinforcement, followed by the shrinkage or the temperature reinforcement. Okay, so this the another important point, that the main reinforcement will be on the top of this slab. Okay, this is the slab. So here we will provide the let me show you that, suppose this is the plan. Here we will provide the and the top. This is the area that we have to provide the reinforcement here. Okay, up to this area, going coming small, then here will be at the end will be the 0, but this let me make it a different color so that it will be easy. Suppose starting from here, the moment decreases, and at the end here it's 0. Here is the maximum, here is the minimum. So we have to provide the main on the top here, and the bottom we need shrinkage or temperature reinforcement for the control of the cracks as well. Okay, so now come to the shear capacity. This is a formula of ACI 31814 section 22.5.5.1, that concrete shear capacity should be 2 into lambda FC prime under root B into D. It should be calculated. We calculate like this for this section. This is 16.6, and applying the pi, and 75%, this 12.5. So this is more than this required. Required is this one, and the capacity is this one, so it's okay. deflection is also okay. 240 L by 240. So it's now done, and we can now uh, make it a simple spreadsheet for any design. Suppose if you want to make it 6 feet, it will be calculated automatically. If you want it make 8 feet, so calculate automatically. This you can make it 3 psi strength. Let's see its results. Okay, now you can see this is the, and then now we made it 8 10. So like the results are like this. 4 inches, 7 inches. Okay, all these are done now, and let's see. This is, suppose we make it 10 now, because before it is for the 8 feet, this is the 9.6, so we should go for the 10 inches. That's why the area is different in all the cases. Okay, thank you so much for watching this presentation. Keep in touch. We will make some short presentation on beam, cantilever beam as well, and torsion reinforcement, how to calculate. Then we will discuss about the simply supported and the fixed supported slabs as well in the next videos, inshallah. Keep in touch. Allah Hafiz.